Hi everyone, I hope you're all healthy and well. Welcome to the next talk in our Golden Webinars in Astrophysics series. Our speaker today is Alvio Renzini, who is Professor of Astrophysics at the Astronomical Observatory in Padova. My name is Evelyn Johnston, and together with Thomas Puzia, we have organized today's webinar for you. As in our previous webinars, we have arranged for simultaneous language interpretation provided by Mr. Patricio Gonzalez, who will be simultaneously translating for us into Spanish. En sus dispositivos pueden escuchar la interpretación al español de la conferencia al pinchar el botón de interpretación que se encuentra en la parte inferior derecha de la ventana de la aplicación Zoom y seleccionar español. We would like to acknowledge the generous support of the Center for Astrophysics and Related Technologies, also known as CATA for its Spanish acronym.
Thank you all so much for all your feedback and comments. If you're watching this recording on YouTube, please leave a comment below if you like. If you would like to support the Golden Webinar series, please send us feedback to our email addresses. If you have any questions during the talk, please type them in the Q&A window so we can select the best questions for the Q&A after the talk. You can also upvote questions and comment on them. Before we begin, we would like to introduce our panel members that are with us today. Of course, Alvio, our speaker, Patricio, Evelyn, and myself. From the faculty of the Institute of Astrophysics, we have Manuela Zoccali with us. We have also our graduate students, Álvaro Valenzuela and Cristóbal Moya with us. And we have also the great pleasure to welcome as our guest panelists today, Claudia Ciccone, who is a professor of astrophysics at the Institute of Theoretical Astrophysics at the University of Oslo. Mario Abadi, professor of astronomy at the Astronomical Observatory of the National University of Córdoba in Argentina. Joel Primack, who's a distinguished professor of physics emeritus at the University of California in Santa Cruz. Mauro Giavalisco, who's a professor of astronomy at the University of Massachusetts. Mike Rich, who's a research astronomer at the University of California in Los Angeles. And Ying-Jie Peng, who is a professor of astrophysics at the Kavli Institute for Astronomy and Astrophysics of Peking University. And of course, we would like to welcome our excellent Q&A managers, Ricardo Acevedo, Daniela Fernandez, and Carol Rojas, who will be going through the comments and questions through today.
It is our pleasure to introduce Alvio Renzini as our speaker today. Alvio obtained his degree in physics in 1963 from the University of Pisa and is Libera Docenza in Astrophysics in 1971 at the University of Bologna. Between 1964 and 1968, he held short positions at the Scuola Normale Superiore in Pisa, the Istituto Nazionale di Fisica Nucleare in Frascati, and the Osservatorio Astronomico di Torino. In 1968, he joined the Università degli Studi di Bologna as an astronomer and was appointed as a professor there in 1980. He stayed in Bologna until 1995, when he moved to ESO in Germany to work as the VLT project scientist.
From there, he retired in 2005, and since then he has maintained a connection with the INAF Osservatorio Astronomico di Padova, allowing him to focus on his research without teaching and administrative duties getting in the way. Over his career, Alvio's research interests have spanned a vast spectrum, many areas including stellar evolution, stellar population in globular clusters, the Milky Way and the nearby galaxies, elliptical galaxies, and the high redshift star formation, and the high redshift universe in general, using theoretical modeling and empirical observations. Today, Alvio will tell us about galaxy scaling relations and the role of angular momentum in galaxy evolution. Alvio, you have our attention.
Thank you, Thomas, and thank you everybody in Santiago for having organized this meeting. I would like to thank in advance the panelists for their support and for their questions if they come. So I think I can start and trying to share my screen and see whether I can retrieve my presentation. So galaxy scaling relations and angular momentum in galaxies and their role on the evolution of galaxies. I must say this is a almost completely new field for me. It's something I got interested only in recent years. So what I'm telling you is not on what I have done during my long career, but rather where I am punching now, where is my personal punching line. And because I think it's more exciting for me to tell you where I am trying to understand new things for me, rather than tell you stories that for me are kind of old. Okay, so the current paradigm of galaxy formation, many of you heard lots of times. It all starts with dark matter halos that grow from tiny initial fluctuations and grow by gravitational instability. Baryons cool inside dark matter halos and start to form stars and galaxies. Star formation and AGN feedback prevents overcooling, because otherwise most of the baryon would be turned into stars in a short time scale, as opposed to the fact that 13 billion years after the beginning, only 10% of the baryonic matter has been turned into stars. So dark matter halos acquire angular momentum via tidal interactions, because there was no angular momentum to start with after inflation. So it has to be built up little by little by tidal interactions. In analytic and especially semi-analytic approach, baryons are then assumed to inherit the same specific angular momentum of their host dark matter halo and start to form galaxies. On the bottom line, you have just three of among the many references one could refer about this paradigm, among those who really founded the paradigm already several years ago. Now the question is that my screen does not change. Okay, it does, but it takes some time. So the theoretical approach to galaxy evolution has in fact proceeded top down, from first physical principles, starting from the mentioned classical papers and all those that followed, and then from primordial perturbations. In this webinar, I proceed in the opposite direction, bottom up, in a purely phenomenological approach, eventually checking to the extent to which the resulting scenario is consistent with theory. In other words, if digging from opposite sides of the mountain, eventually we meet in the middle of the tunnel. So let's go now and see how high redshift galaxies look like from, let's say, from cosmic noon at redshift 2 to the present. Most of the star-forming galaxies at redshift 2 are already rotating disks. And you can see here this plot was taken from Wisniewski of a year ago. And what you see here is in a plot of star formation rate in the y-axis versus stellar mass on the horizontal axis. You have each galaxy is represented by its velocity field. And you see that most of them are red on a side, blue on the other, indicating that they are kind of orderly rotating disks. So kind of 70% of the galaxies are already settled into ordered rotation by redshift 2. And when we come to redshift 0, basically the vast majority of the star-forming galaxies are in fact thin rotating disks, not dissimilar from our Milky Way. On this plot, you also see that most of them have, I mean, at redshift, still at redshift 2, have well-behaved rotation curves, and this will be the case of course, at even lower redshifts. Now, these galaxies at high redshift are smaller. For given mass, if we measure the size of galaxies locally, and then we measure the size of galaxies at higher redshift, provided we pick up the same stellar mass, they are smaller, as indicated in these plots from one is from Maula et al., the other from Van der Bijl, but I could place here a lot of similar plots that qualitatively, at least, they agree. They don't never necessarily agree perfectly quantitatively. I will return on this point later on. But basically, that's the situation. Here you have in red, this refers to the quenched galaxies, to ellipticals, to galaxies that have finished to produce new stars. And the blue symbols instead refers to the star-forming ones. And this is in fact what I am talking today, is about the star-forming ones. I wouldn't say much about the quenched galaxies at all. At high redshift, star-forming galaxies are more gas-rich, as you can see on the left panel in this view graph from a review paper by Linda Tacconi and others. And you have that as we go to high redshift, for fixed stellar mass, galaxies are far more gas-rich. This is on a log scale, so it says that by redshift 2, the gas content and the molecular gas content, because this is what we can measure at these high redshifts, is more than a factor of 10 higher for given stellar mass than in local galaxies. On the right side, you have instead the traditional star formation rate stellar mass plot for different colors refers to different redshifts. And you have that, in fact, at high redshift, star-forming galaxies are more star-forming. Their star formation rate increases as we go to high redshift for fixed stellar mass. Of course, the stellar mass of a galaxy is not fixed as it evolves, but this is just measuring properties of galaxies, having selected the galaxies with the same stellar mass at different redshifts. In this view graph, basically you have a summary of what I just showed with the figures. That is, the galaxies are disks, they are smaller, they are gas-rich, their surface gas density, therefore, is substantially higher because they are more gas-rich and they are also smaller. And the star formation rate is much higher. What you see here are also simple power law of 1 plus z, capturing the trend of these basic galaxy properties with redshift. And we will return a lot about several times about these values. Let me just emphasize one point. The fact that the gas increases the fraction of the gas, the molecular gas mass over stellar mass increases with the power 1 plus z power 2.6, whereas the radius gets smaller as 1 plus z power minus 1, implies that the surface density of the gas evolves with redshift with a very high exponent, as I mentioned, 1 plus z power 4.6, which is to say the surface density of gas in high redshift galaxy, I mean at redshift 2, is 150 times higher compared to what it is in local galaxies of the same mass. Just to give you a feeling of how different are galaxies indeed at high redshift. And also we can, from the difference in these exponents, we can infer that the star formation, not only the galaxies are gas-rich, are more gas-rich, and are more star forming, but also the ratio of star formation to gas mass is higher, which is to say that they are able to convert gas into stars more efficiently than local galaxies. This is just to introduce some of the, these are not all the scaling relations we may think of galaxies with redshift, but are just those I will use in the following. Now, having presented the relations at fixed stellar mass of galaxies, let me now turn to instead trying to follow an individual galaxy as it evolves from redshift 2 all the way to redshift 0. It will increase in size, in mass, and in other dynamical properties I will mention in a moment. And how much does a galaxy increase in mass as it evolves, as it grows, and because it forms stars and so on? One way to estimate it is, in fact, to integrate, since we know the star formation rate as a function of time and stellar mass, we integrate this relation and follow, as we know, the rate at which they form stars, we know the rate at which they grow, and we can figure out the typical growth factor of a galaxy from redshift 2 to 1. And the result is a factor about 10, with one proviso, however, which is the following. The result of this integration is extremely sensitive to the precise normalization of the relation of star formation rate with stellar mass. A small difference tends to amplify, and therefore I will not take this result factor of 10 as really a solid and extremely well established number. An alternative way to estimate a typical mass increase of a galaxy, or the mass increase of a typical galaxy, is by noticing that the stellar mass density increases by a factor of about 4 from redshift 2 to 0. That is, 10 billion years ago, only about 25% of the galaxy, of the stars were in place. And so 3/4 had to be made in the meantime. This factor of 4 growth for individual galaxies has to be taken as a strict lower limit to the increase in stellar mass of those galaxies that manage to remain star forming all the way to redshift 0. Because many galaxies in the meantime, during the intervening 10 billion years, quench and cease to form stars, and therefore give up, cease to contribute to the increase in stellar mass of the universe. So I adopt eventually somewhere between a factor of 4 lower limit, a factor of 10, which is perhaps an upper limit. So, but that's the range, I would say, where it's reasonable to pick up the number. And I may take a factor of 8 indicatively, 6 to 10, something like this. In parallel, if the size increase as the scaling relation that you see there, I have to remove your faces in order to see the rest of the view graph. If the effective, the half mass radius increases, as you see at the bottom of this view graph, by redshift 2, the increase is a factor of 4.5 since redshift 2. One because the factor of 3 because 1 plus z minus 1, and the other because there is the mass increase which contributes another factor of 1.5. So let's start to put together these numbers, say the mass increase and the half mass increase. And the third quantity I want to is its rotational velocity of galaxies. The typical, and because what I am interested in, as the title of my webinar was saying, the quantity I want to talk today is the angular momentum of the galaxies. Now, the angular momentum is proportional to the product of three quantities: the stellar mass, the half-light radius, the size of the galaxy, and the rotational velocity. And a scaling rotation for the rotational velocity, in a sense, is shown in the plot on the left from Simons et al. Of a few years ago, in which by redshift 2, the rotational velocity increases by roughly a factor 1.5. So if you make the products of these three quantities, a factor of 8 in mass, 4.5 in size, 1.5 in rotational velocity, you end up with a factor of 50. 50 is really a very scaring number. And in fact, I'm not sure it is correct. I may say that perhaps it's an exaggeration. If I take a more prudent estimate for the increase in size, I may go down somewhere. But let's say I find it difficult to think that it is substantially less than 20. And let me take this number as indicative. The same kind of exercise was made also by Natasha Forster-Schreiber and Woutz in an annual review paper from where I pick this view graph, in which the wavy borders and the hand-drawn lines just indicate that it's still tentative to some extent, but it captures the trends, the main trends. Also here you can see how much over the last 10 billion years the size, the stellar mass, and the angular momentum have increased of a typical galaxy. In this case, would be a galaxy that by now would be similar to the Milky Way. So we have this large increase of angular momentum. And this increase in angular momentum is not just due to the increase in mass, but also the increase in size and in rotational velocity, which is to say that if you divide by the mass, what you get is the specific angular momentum or angular momentum per unit mass, and also the specific angular momentum per unit mass is increasing with time. How to ensure that over 10 billion years, the angular momentum of a galaxy grows steadily by such big factor? I think the following two bullets tell how I think things have to go. That is the angular momentum of the inflowing gas, the gas that feeds the galaxy, because galaxies need to be fed. This must increase with time, over 1 Hubble time consistently. And it must come in basically on the disk plane and co-rotating with it, breaking symmetry between materials coming, rotating and counter-rotating. Because if this kind of symmetry were maintained, there would be no growth in angular momentum. So the conclusion, just from the result, this estimate of the angular momentum growth of galaxies is that the first, to some extent surprising to me at least, it was surprising, that it is the vorticity of the circumgalactic medium that drives the growth of galaxies. Do we have any direct evidence for this? Well, over the years, there have been complete agreement among all practitioners on galaxy evolution that galaxies need to be fed continuously, as I alluded a moment ago. And this is because the depletion time for their gas content, that is to say, the amount of gas divided by the star formation rate, is much shorter than the Hubble time. So they will all be dead by now. Instead, they are not. So the galaxy need to be fed. There has to be an inflow of gas. But so far, it has been very hard to see it. There have been lots of evidence for outflows, but not much for inflows. But things have started to change in recent years, and I would like to show you a couple of examples. And these are results by Ho and Martin of last year, basically, in which they have looked at magnesium absorption over the spectrum of a distant quasar in galaxies at redshift about 0.2, 0.3. And they were able, via imaging, to figure out the direction of rotation of a galaxy by the way the spiral arm wind up. And what they found is that for absorbers, for quasars that lie along the major axis of galaxies, they are all co-rotating. The material, all the way to a distance of almost 100 kpc, is co-rotating with the central galaxy in 12 out of 12 cases of their study. So this sounds in agreement with what we would expect from the estimate of the angular momentum increase from the scaling relations. A similar result at somewhat higher redshift has been also obtained by Zabel and Boucher. And what you have here is, on this plot, is on the left, you have the rotation curves of a sample of galaxies. And on the right, look at the stars in the middle of these vertical bars. The stars are the rotation, the velocity in measured by the absorbers in the circumgalactic medium of these galaxies. And again, you see that in 7 out of 9 cases, the absorber is co-rotating with the galaxy all the way to more than 60 kpc from the galaxy. Now, this, as far as I know, is all I know about the empirical evidence of co-rotation of the circumgalactic medium from the observational perspective. But let me now turn to the modeling, to the hydrodynamical simulations, because I would like to show you this result by Buck et al. Very early this year, in which you see here are 5 model galaxies, and what they are labeled by the mass of their dark matter halo at redshift 0, so after 13 billion years from the beginning. And what is plotted here, you have to pay attention what is on the abscissa. This is the ratio of the z component of the angular momentum over the angular momentum for the material that is rotating with the circular velocity. And this refers to the stellar particles in the simulation. Different colors refer to different redshifts. A yellow is redshift 4, and dark blue is redshift 0. So what you can notice, especially in the middle one, just to focus on one of those, is that at the beginning, the distribution of angular momenta is symmetric respect to the 0, which means that there are as many objects, as many stellar particles that are rotating one way as there are that are rotating the opposite way. And this is the epoch, in fact, of chaotic assembly of galaxies, merger dominated, so for saying. But you see that by redshift 2, this symmetry starts to be broken and eventually dramatically broken, because what you have in the end is almost a delta in which everything rotates at its circular velocity. And that's beautiful. When I saw this, I said, gosh, that's really what I was looking for. And so, indeed, in this simulation, at least, the streams come in planar and co-rotate with the rest of the galaxies and build up a disk of an Hubble time. The one on the left, which is, by the way, the least massive, does not behave as well. It's one case in which is suffering a lot more of mergers all the way to the present, and in fact fails to develop a well-ordered rotation. Sorry. Now, other results from simulations are mentioned here. So having come to the conclusion that the circumgalactic medium vorticity dictates the angular momentum history and the growth in mass and size of main sequence galaxies that stay on the main sequence from high redshift to the present, then let's go again to see what the results are of hydrodynamical simulations. Stewart et al. Analyzed a bunch of different simulations from different groups. And the generic result was that, contrary to an old postulate, the inflowing baryons carry 4 or 5 times more specific angular momentum than dark matter halos. So this postulate, that was the obvious thing to do when we didn't have more to play with, that baryons share the same specific angular momentum of dark matter. This is not confirmed once the proper hydrodynamical simulations are performed. And more recently, actually, the first to hint for this was a guy called Pichon from France. And now you have a bunch of other papers that you see here in red, all finding basically the same. The baryons carry more specific angular momentum than dark matter halos, at least in the vicinity of successful galaxies. So, moreover, in those simulations, as we were wishing to find, the flow is largely coplanar and co-rotating with the disk. There is this order in nature, so for saying. I have not seen, if you look to the bottom bullet, I have not seen widespread, at least, a comparison of say, an estimate of the growth of angular momentum of simulated galaxies. And essentially because from the observational side, there has not been a stimulus, perhaps, for the theoreticians to produce this kind of quantity. But it is certainly in their computers. It's still in the it's still in the results. Now, I have been much in doubt myself about the factor of 50 or 20 about the increase in angular momentum. The most uncertain ingredient in this estimate, in the three factors M star, RH, and V rot, is in fact the size. It looks strange in a sense, because measuring the size seems to be a trivial affair, and apparently it is not quite so. And let me mention here other results in which they find milder evolution with respect to what I had assumed. Let's say the exponent of 1 plus z could be substantially smaller than, or different from -1, could be minus 0.5 or even minus 0.4. So I'm to say that it is not, there are discrepancies among the various estimates in the literature, even in the recent literature. In fact, let me mention here JWST, because having better resolution in the near infrared, in the B band, and even in the 3 or 4 micron than HST in the H band, it will be possible to measure the half mass radii of high redshift galaxies far better than it's been done with HST so far, not for saying from the ground. Now, one critical issue, because you can find different schools of thought in the literature, is whether the accretion of gas onto galaxies, whether it is coplanar and co-rotating, or is it kind of a rain falling perpendicular to the disk from both directions, from the north hemisphere and the south hemisphere alike? Because this has been historically the way infall has been thought by many researchers. And several of them perhaps keep thinking in these terms, as opposed to ordered streams that feed the rim, the outer rim of galaxies, as opposed to fall on top of disks from all directions. So that's this is an open issue. I am inclined for the first solution rather than the second, for the reasons I mentioned. But that's an objection that may be worth discussing. Well, at some point, as you know, galaxies quench, and you know, in the sense that they give up forming stars, and various candidates that you see in the view graph have been entertained in the literature, and still we are undecided on which is the dominant mechanism to stop star formation in galaxies. So the question I try to ask myself is the following. Does angular momentum have a role in quenching? An ansatz we put together with Yingji Peng earlier this year is the following. If the angular momentum of the inflowing material is increasing systematically, secularly with time, eventually the inflowing gas may settle into a too high angular momentum orbit for to eventually penetrate inside the optical disk of galaxies and transform into H2 and feed the star formation. If this happens, that is, if at some point the angular momentum is too high, maybe the inflowing material is not able to feed the galaxy anymore. And in this view graph, what you have is for local galaxies, basically for Sloan galaxies, or SDSS galaxies, you have, as a function of star formation rate for galaxies in the mass range, in a narrow mass range between 10.6 and 11 in the log, you have the gas mass separately for the molecular H2 and the atomic H1. And you see that as a galaxy tend to quench, that is, if as the star formation rate decreases, the molecular gas tends to vanish, but the atomic gas stays flat, stays the same, at least down to the limit of this low star formation rate. Those galaxies are not fully quenched. They may qualify as to be so-called Green Valley galaxies. But the hint is that, in fact, galaxies quench when they run out of molecular gas, while still maintaining, at least for a longer time, atomic hydrogen reservoir. And the same result is by Hunt earlier this year. We have for massive galaxies, only what is pertinent part of the plot is inside the circle that you see there. That is, again, the molecular gas drops as the star formation rate decreases, whereas the atomic gas stays nearly constant. An example of what may be an object of this kind is this galaxy NGC 1543, which is basically a dead S0 galaxies that is surrounded by a nice H1 ring that rotates, as you see from the right side plot in blue and red. So let me approach the summary of my talk. So I have argued that the scaling relations suggest that the angular momentum of individual disks has increased by a very large factor over the last 10 gigayears. And this suggests that, and at the beginning, they were not, as you have seen in that simulation, they were not rotating much. I mean, they were still in a phase of being symmetrical. I may argue that the star formation and galaxy formation started in minima of the angular momentum density in the baryon distribution, because it's easier to collapse if you don't rotate at all. And that's perhaps globular clusters that are very compact and not much rotating objects at all may be something that the early universe was so prolific in globular clusters, perhaps because of there was not much angular momentum at the time. Now, the angular momentum distribution of the circumgalactic medium, I argued, is a key factor in driving the evolution of galaxies. This is, I'm sure, not new at all if you proceed top down from first principles, I would say. But it's nice to find it empirically in this completely bottom-up approach. The other interesting aspect is that the angular momentum of the circumgalactic medium has to remain within some limits for a successfully growing disk to be produced. In other words, I will expand on this, making two opposite extreme examples. But let me add here another consideration. Cooling has been often considered to be the key factor in driving galaxies, in promoting the galaxies say, the gas accretion into galaxies and so on. And lots of plots have been made finding where the baryons can cool and where they cannot cool and so on. But cooling is just one aspect of feeding galaxies. The baryons need to cool in order to be properly accreted and eventually turned into molecular hydrogen and into stars. But also the gas that is accreted into galaxies carry its own angular momentum, and the angular momentum is the other aspect of the accretion. So, and this, I don't think, at least for my direct experience or exposure to the literature, which is certainly limited, this aspect of the angular momentum accretion has not been, say, as widely entertained as the cooling or other aspects. Now, let me come to expand on this concept that galaxies grow only where the circumgalactic medium has a specific angular momentum within some limits. The idea is, qualitatively, is just the following. If at some point the circumgalactic medium is the angular momentum of the circumgalactic medium is too high, a galaxy may starve and quench, as I said before, because no hydrogen is converted to molecules. On the other hand, if the angular momentum is too low, a blue nugget may form, that is, a very compact star-forming object that may soon quench as well. So the condition for success must be, however, widespread, because so many galaxies have populate the main sequence, they are disk, they are well behaved, and therefore it means that this condition of having the right vorticity of the circumgalactic medium must not be a very rare event in nature, but must come sufficiently enough to account for the fact that we have so many nice galaxies in our universe. So to conclude, the vorticity, indeed, of the circumgalactic medium is a major driver in galaxy evolution. Galaxies grow where the circumgalactic medium has the right vorticity. This may be a trivial aspect, but let me finish this talk with a message, so for saying. I have read hundreds of papers on the star formation history of galaxies, but very few, if any at all, on the angular momentum history of galaxies. And I think this is a concept, an aspect that deserves more attention, and I'm sure there will be more attention on this aspect, especially on the observational point of view. And it is just because observing the star formation and the mass of galaxies is far easier than measure its angular momentum or the angular momentum of the circumgalactic medium. That is very hard in observations. It is easier in simulations, although even that is kind of difficult because, as you can imagine, when an hydrodynamical simulation with so many cubic megaparsecs of universe being produced to produce mock galaxies, it's not easy. I can imagine, and something I never did myself, but to go into the numbers stored in the computer with the old simulation and try to extract maps of the vorticity of the baryons around individual galaxies. It's almost, I would say, as difficult as for the observers to do it. but the numbers are there. So I think that's the end. I hope I have been inside the limits. And so let me thank the audience again for their attention. Thank you.
Thank you very much, Alvio. Let's go to the questions. So I think Manuela had a question.
Yes, thank you, Alvio, for such a great talk. I would like to expand to one of your points in the summary. If at some point the infalling gas is not coplanar and co-rotating, what would you think will happen to the galaxy? Would that be a channel to make an elliptical alternative to merging, for instance?
Well, if no, I don't think it would make an elliptical. Certainly, if there is a pre-existing gas disk and the inflow is substantial, so you have a counter-rotating accretion, this may trigger info, and lots of material may fall to the bottom of the potential well, that is to the center of the galaxy. You might have a disk instability, eventually producing a central burst of star formation and making or growing, if not there, a bulge, rather than. So the elliptical galaxies, presumably they form from dry mergers, from mergers that are from objects that had already been quenched. A wet merging, that is the merging of two gas-rich galaxies, or the arrival of counter-rotating flow, I would say would shrink a galaxy because it reduces the global angular momentum of the galaxy, and would promote lots of star formation and may help forming, growing a bulge.
Okay, let's go to Joel next.
Hi, Alvio. Very nice talk. A good summary.
Hi, Joel.
I wanted to mention a number of papers that Avishai Dekel and I and our group have been writing over the years that did what you basically asked for. So one paper to start with is Mark Danovich et al., 2015, where we traced in great detail with high-resolution simulations the evolution of angular momentum of the vicinity of galaxies and also of the galaxies themselves. What we found in many high-resolution simulations is that something like a third of the simulations produce exactly what you described, a very rapid infall of gas to the center because of counter-rotating streams. Roughly half of the time that happens in high-resolution simulations is due to mergers, both minor as well as major mergers. These kinds of statistics are discussed in the Danovich article and in some of our subsequent articles. A paper that was just published last year, led by Fangzhu Zhang, Jiang, also part of the Dekel group, looked in detail at this question of the relationship between the angular momentum of the dark matter halo and the size of the galaxies produced by high-resolution simulations. In our own simulations and also in the Nihao simulations, the Buck paper that you mentioned is a high-resolution Nihao simulation. What we found was that there's no correlation whatsoever, none. It's a complete scatter plot between the angular momentum of the dark matter halo and the size of the resulting galaxy. So as you suggested, the baryonic effect, the amount of angular momentum that's actually brought in by these streams is a very major factor, but is not directly correlated with the angular momentum of the dark matter halo. Now that raises an interesting question. What is it that determines the radius of galaxies, at least in high resolution simulations? And the answer is that to a first approximation, it's the size of the angle of the dark matter halo itself. Andrei Kravtsev, in an article in 2013, FJ Letters, showed that there's an excellent correlation between the size of the galaxies, and this is true for elliptical galaxies as well as disk galaxies, and the radius of the dark matter halo. But there's still a fairly big dispersion. And then the question is how, and then in a follow-on paper led by Rachel Somerville, my former graduate student who's now a leader in the field, we followed this out to redshift 3 using the Candles data from Hubble Space Telescope. And we showed that to a good approximation, the same is true. But then the next question is, okay, how do you account for the dispersion around the radius being the radius of the halo times about 2%, 0.02? And the answer is, in the Zhang paper, it's actually the concentration of the dark matter halo. High concentration halos form early, accrete at higher densities, and their centers are high density. I just want to make one last comment about a paper from our group, and that is a paper led by Avishai Deckel that was just published a few months ago. And what it shows is that at early times, the angular momentum fluctuates a lot as different streams are coming in. And as a result, gaseous disks don't form, or if they do form, they're very thick and warpy and so forth. But there's a simple criterion. Once the dark matter halo mass exceeds about 2 times 10 to the 11th solar masses, then the rate of mergers slows down and the spin flips decrease. And that's when you get this phenomenon that you nicely described, where you get a long period of gas coming in, coplanar, and bringing in a lot of angular momentum. So sorry for this long introduction to a bunch of papers, but some of us have actually been looking at exactly the question that you raised. How does the angular momentum get into the galaxies, and what does this have to do with the radius of the galaxies? So I thought it'd be useful to refer you to those papers.
Well, no, yes, I have quoted some of the papers. I think I had a paper quoted by Avishai on my biograph, or at least it was at some point. Yeah, of course, I am very familiar with not all the theoretical literature, I must say, but those with you and Avishai substantially more, essentially because there is an attempt to isolate specific aspects of galaxy formation and evolution, such as the cold streams paradigm, for example, as opposed to merging as a driver that that Avishai and your group has developed, is something that was very clear in my mind. I mean, however, I think you will appreciate that I came to these conclusions without need of simulations or theory, but just from the observed numbers.
Yes, indeed. But you also said that we theorists should be tracking the angular momentum of the material that comes in. And I just wanted you to,
yes,
to know that
yes,
in a
okay.
number of papers we've
Okay,
done
no, I know
that.
I didn't want to imply that the angular momentum, nobody has worked at this aspect. That's certainly not true. Certainly not true. Okay.
Okay, let's go to the Q&A. So we have a question from Mladen Ivkovic, who's asking, how would one observe the angular momentum history of galaxies? What would be the observable quantities?
Well, if the question is about of galaxies as opposed to the circumgalactic medium, well, one has to measure their mass, their radius, their size, their mass distribution inside, in case, and their rotational velocity. These are the three quantities that define the angular momentum. These are observables. We can measure it. Measuring the vorticity of the circumgalactic medium, which is the agent for the growth of galaxies, is far more difficult because we can, so far it has been observed basically only in absorption of observing a quasar which is behind the outskirts of the galaxy, and only few cases have so far been, the one I have mentioned, by the way, have succeeded to measure the vorticity of the circumgalactic medium. But we may hope that more will come in the next years.
Thank you. So let's go to the top of the Q&A. We have, well, it's just jumped down. We had a question from Gaspar Galaz. So low surface brightness galaxies exhibit a general high specific angular momentum, and on the other hand, they have large fractions of dark matter. Is this consistent with your affirmation that baryons carry more angular momentum because low surface brightness galaxies have low amounts of baryons, or is it consistent because they're H1 rich?
I don't know. That's the simple question, a simple answer. I mean, I would say this issue about the specific angular momentum of the baryons exceeding that of the dark matter refers to well-formed typical galaxies. When we go to low surface brightness galaxies, these are definitely different objects that might have had a totally different, in fact, they are so different, they must have had a totally different formation history and structural transformation. So, yeah, definitely my statements taken from those papers I referred to are concerned these typical galaxies as opposed to low surface brightness galaxies.
Okay. Okay, let's go to Michael. He's got his hand up.
Yes, just a quick question about how the most massive galaxies that form very early on at redshifts higher than 4, how they fit into this picture along with supermassive black hole formation.
Yes, in one of my bullets, there was this idea that the first objects form in minima of the specific angular momentum distribution of the baryonic matter. To form a black hole, we really need a very low angular momentum to squeeze 10 to the 9 or 10 to the 10 solar masses inside the spatial radius. You see, one really needs to have low angular momentum. So yes, the big galaxies, apart from the central supermassive black holes, but the massive 10 to the 11 solar mass galaxies at redshift 4 or 5, there are few of them by good fortune, and so they are very rare objects. But it's likely indeed that they formed under conditions where in those spots where by chance, by the vagaries of the universe, so for saying, it did happen that the angular momentum was very low and material could easily collapse and form a big galaxies. That, I mean, when you have a lot of angular momentum, it's not easy to produce compact and massive objects, of course. And
conditions wouldn't be present later on, which is interesting. Unique situation.
Yeah, that's another good point indeed, Mike. That is, yeah, this brings me to make another point. That is, at the beginning, let's say, after recombination, there is not much angular momentum field at all. It has to grow, and as the structure grows, so grows the angular momentum, which is therefore a secondary effect to the growth to the formation of halos. First you form halos, and then you have the halos to tidally interact with each other. No? So angular momentum grows with time. The density, the angular momentum field of the baryons has to grow with time. And that's why galaxies grow, in fact, I would argue. And indeed, that's to connect to your initial point. At the beginning, there is less angular momentum, and therefore it's easier to form compact massive objects, while it becomes harder to do it later because there is too much angular momentum in the end.
Oh, let's go to Mauro next.
So 2 comments and 1 question. So the 2 comments are these. The idea of trying to test whether the accretion of gas onto the disk on the galaxy is perpendicular to the plane or coplanar, maybe can be tested by looking at the evolution of the star formation rate profile, ideally in the individual objects, but that's quite difficult also, but at least in the population. And also, comments number 2, at looking at the evolution of the metallicity radial profile. Maybe the metallicity radial profile encodes the way the gas has accreted. We just published a paper. We're about to post a paper on that measure in particular, metallicity of the gas phase in star-forming disks. The question is the following, Alvio. The same empirical results that you quoted, where you reported that secularly disks evolve by increasing their velocity, rotation velocity, also reports the disk evolves by reducing their overall velocity dispersion. So disks evolve by rotating faster and becoming colder and colder, apparently. Is this evolution of the velocity dispersion consistent with your idea of accretion being coplanar at some point, failing to transport gas to the center and thus quenching the galaxy?
As you say, yeah, definitely the velocity dispersion decreases from an order of 60 or 70 kilometers per second at redshift 2 down to 10 or 15 kilometers per second at redshift 0 in a typical Milky Way mass galaxies, let's say. I don't know to which extent the accretion, the interaction of accretion with determines, I mean, the velocity dispersion, or if there is any connection between the two. Probably there is. I don't have a quantitative answer to your question. I think that the tendency is for disks to get, as you say, thinner and thinner, perhaps because disturbances tend to decrease with time. The star formation rate is decreasing. The surface density of gas is decreasing, and so everything is getting quieter in a sense. In fact, we don't know still what is the origin of the high dispersion at high redshift, whether it is the star formation itself that pumps the gas, or whether it is the inflow of material, the falling of material. And there has been several papers, especially from the MPE group, about this, but there is not a definite answer about the origin of the velocity dispersion. Maybe all these candidates together contribute.
Okay, I think Thomas had a question.
Yes, I have a great talk. Wonderful overview. I wonder whether we should talk a little bit more about the AGN activity in these galaxies and whether basically the feedback mechanisms induce sort of an asymmetry and impinge or impose on the CGM certain anisotropies and angular momentum preferences, let's say, in the assembly of galaxy disks in the early days, right? So the question would be, do we have any understanding of how overmassive the black holes, the supermassive black holes in massive disk galaxies today are that have, let's say, over average angular momenta, specific angular momenta? And that's the case, then I would argue that AGN feedback is a very valuable mechanism to actually evacuate the cones that you had in your model, beautifully depicted there, of these angular momentum vectors.
Yeah, those are this cartoon that Nicolas Boucher has promoted, and that captures, in fact, the geometries, if not else, of what we think is what is going on. Yes, the bipolar flow, so for saying, can have two origins. One is, in fact, just the star formation. I mean, it's easier. We have evidence, empirical evidence of galactic winds that those which up to a velocity of about 400 or 500 kilometers per second are driven by star formation itself, and the star formation and the flow is more evident for galaxies above the main sequence because they have more star formation. On the other hand, especially when one goes to high mass, another kind of flow, of outflow, is found empirically. That is a nuclear outflow that originates from the nucleus and runs at 1500 kilometers per second. And these events are found especially in massive galaxies. This is shown in a nice paper by Natasha Foster-Schreiber of last year. You know that AGN feedback has been widely entertained as a driver for quenching, as the basic mechanism for quenching. And may well be that that all the candidate quenching mechanisms at some point give their contribution to turn galaxies into quenched state. However, about the central outflow, you know that there have been two scenarios for AGN quenching. One is ejection. I mean, the AGN becomes a very powerful quasar, so that blows away the gas from the galaxy. And the other is instead is the so-called preventive quenching, in which jets or high velocity winds from the nucleus have the effect of heating the circumgalactic medium, then preventing it from cooling and feeding the galaxy. I think the second mechanism, it's my feeling, is more credible for a simple reason, that AGNs go through periods of activity interleaved with long periods of total inactivity. And so they might have thousands of such activity cycles in the course of their growth. And yet it means that for 1,000 times they don't quench. The galaxy keeps going. It's only one final shot that quenches. Does not look so attractive to me. Instead, the preventive quenching is something cumulative. You have that you can have 1,000 cycles, but each contributes to heating the circumgalactic medium. It's something cumulative. And eventually, once enough has been accumulated, this may turn into quench. Of the two scenarios, that sounds to me more attractive. And about the quenching by angular momentum, I think what we would like to see is the following. I have shown that this plot from Zhang, Peng, et al., in which you have the molecular hydrogen falling down with star formation rate, whereas the atomic hydrogen stays constant or thereabout. Well, those observations are made with Arecibo, and Arecibo does not have at 21 centimeters the spatial resolution to figure out where the hydrogen, the atomic hydrogen is located. Is it within the optical body of the galaxy, or is it in an outside rotating ring that does not participate, in fact, in the star formation activity? And for this, one needs more high resolution observations at 21 centimeters.
Unfortunately, not with Arecibo anymore.
No, one needs an interferometer.
Thomas?
Should we go to Mario?
You see,
Sorry, how are you?
No, okay.
Sorry.
No, go ahead.
No.
Okay. Thank you very much for a very nice talk. I was wondering why the angular momentum of the baryons keeps growing with time. In the tidal torque, according to the tidal torque theory, the maximum of the angular momentum of the dark matter halo happens at very early on in the turnaround. It's just because the baryons collapse very late?
I don't know. The question, perhaps Joel may know, because it's only those having made the simulations that have been exposed to the problem. And the results, all the simulations agree that the angular momentum of the baryons, basically the baryons are decoupled from the dark matter halo, at least around successful galaxies. Maybe that there are halos that are inert, that don't form much galaxy at all because the baryons have different kind of behavior. That might, I mean, the nature may be manifold in this respect. But yes, the question is why the baryons don't follow dark matter as far as the angular momentum is concerned. I can only say, I can only welcome this because I have been a sympathizer of the baryon liberation movement myself, but I don't know why. So perhaps Joel may say.
Well, I can just comment that the baryons that feed disk galaxy evolution are coming on these cold streams from the cosmic web. They tend to flow down filaments, and they are coming often from a considerable distance, and they're coming in with a fairly large impact parameter, which increases their angular momentum. Incidentally, amusingly, in simulations, they come in not ballistically. In other words, they don't speed up as they come in. They come in at more or less constant velocity. And we and others have attributed this to the fact that they're constantly losing energy by Lyman alpha radiation at more or less the same rate at which their gravitational energy increases as they're moving deeper into the potential well. And this is what powers at least part of the Lyman alpha blobs that we see around galaxies. But the key point is one that Alvio made in a couple of different ways, including in his latest remark, and that is that there really is a decoupling between these cold streams and the dark matter halo. the cold streams are coming in from outside the halo, and they're coming from larger distances. As I said, when one looks at a number of simulations, it's not just our simulations and the Niehaus simulations. The TNG50 simulations show the same thing, that there's essentially no correlation between the dark matter halo's angular momentum and the angular momentum of the gas that ultimately makes the disk of the galaxy. Let me add one more thing, and that is that we're working within a paradigm called cold dark matter, or lambda CDM, with some sort of dark energy like a cosmological constant. And that means that we're assuming that there's essentially a Gaussian distribution around the fluctuation spectrum median. And so that means that there will be some halos that form early that have a high overdensity. These will tend to occur in regions where there are other high overdensity halos, in other words, a high density region. The early universe, of course, has much higher density. The density of the universe is dropping as 1 plus z cubed. Sorry, as 1 over 1 plus z cubed, as scale factor cubed. And the result is that galaxies that form at high redshift are forming in these very dense halos. And so very naturally, they're going to be extremely dense objects. They can subsequently accrete, but what often happens is that they're in such high density environments that a cluster starts to form, and that cuts off the gas supply. That's the fact that one has this Gaussian distribution with a rare number of rare peaks, but they are quite significant peaks, helps to explain how you can get galaxies forming at high redshift. As far as we can tell, this fundamental Gaussianity, which may come from the physics of cosmic inflation, is perfectly consistent with all the observations. We don't need this strong evidence against non-Gaussianity, both from the cosmic microwave background and also the fact that the simulations do seem to be able to reproduce the history of star formation pretty well.
Okay, let's take one final question before we wrap up. Let's go to the Q&A. There's a very good question that's risen to the top by Dietrich Bader. If disk galaxies grow in angular momentum by as much as you said, they should be roughly aligned with the CGM vorticity. Could anything be learned about cosmogony from, I'm assuming that's cosmology, from the angular momentum vectors of disk galaxies as tracers of vorticity and the evolution with redshift?
There is a number of papers in which they try to relate the angular momentum of a galaxy, the angular momentum vector of a galaxy, with the filaments to which they belong, to see whether there is an alignment of galaxies with the filaments. They find a signal that is, there is a tendency to be aligned, but it is very minor. It's an effect of 10 or 15% of galaxies seem to be aligned with the filament. There are only a few papers that have attacked this issue, essentially because it's kind of difficult to identify filaments in the first place. And then also, yeah, so the result is that there is, so this is not precisely the question that Dietrich, you have asked. That was whether there is an alignment of the circumgalactic medium with the galaxy. I answered about the filaments because that's where people have been looking for. About the circumgalactic medium, the only evidence I know is the one I've mentioned. The fact that these absorbers appear to be co-rotating in this 12 out of 12 cases at redshift 0.2 and in 7 out of 9 cases at redshift 1. That's the only direct empirical evidence of a co-rotation of the CGM with the galaxy.
Actually, there's a very recent paper that I think addresses this quite clearly and sees a very strong signal. It's a 2 sigma signal or greater. The paper was led by Charlotte Welker, and it's an observational paper based on the SAMI galaxy survey. The title of the paper is First Detection of Transition and Spin Orientation with Respect to Cosmic Filaments in the Stellar Kinematics of Galaxies. The key sentence in the abstract is that this supports a scenario of early angular momentum buildup in vorticity-rich quadrants around filaments of low stellar mass, followed by progressive flip of spins orthogonal to the cosmic filaments through mergers at high stellar mass. This has been the scenario in simulations for years. But this is an observational paper. They do recover the filaments. It's not trivial, but they do it. And they see what looks to be quite a strong signal. It's exactly what we had expected from simulations. So perhaps as a simulator, I'm more prepared to believe it.
In terms of sigma, that is, it is definitely detected, but the amount of alignment is still small.
Well, there's a tricky aspect, and that is that the pattern that we had expected is that the angular momentum would be aligned with the filament at earlier times, and then flip and become perpendicular to the filament as a result of mergers. So that makes the signal tricky to find, but that's exactly what Charlotte Welker et al. Found. Incidentally, I'm not a co-author of the paper. I'm just an admirer of it.
Yes.
This is observational evidence.
I know. I think I have even quoted one of those papers in my recent paper about these issues. Yes. No, I am aware of the result, in particular also about the flip at high masses due to merging. Yes, I was knowing about that. But it may be, since there is not such as I said, the alignment has been found with high statistical significance, yet the signal is small, which means that what makes the angular momentum of individual galaxies is probably something that takes place at a space in a volume which is smaller than the filaments. The filaments have an influence of it, but it must take place, say, the origin of the angular momentum that makes galaxy has to take place at a scale smaller than the filaments themselves. That I would guess from the fact that the signal is small, as opposed to having all the galaxies perfectly aligned with a filament.
Okay, let's wrap up there. We can continue this conversation away from the webinar. So yes, thank you very much, Alvio, for telling us all about this, and thank you to everyone for joining us for Alvio's talk. At the end of the webinar, a survey will pop up, so please be so kind as to fill it out and give us some feedback. And our next scheduled talk is for next Friday, December the 4th, which will be given by William Press, who will be leading us on a quick dive into computational finance. For now, though, stay safe, stay healthy, and we'll see you at the next Golden Webinar in Astrophysics.
Thank you.